Hey everyone, in this video let's take a look at question 23, merge k sorted lists on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question you're given an array of k linked lists, which is called lists, and each linked list is sorted in ascending order. We want to merge all linked lists into one sorted linked list and return it. So in our example here, we're given 3 linked lists, and you can see that they're all sorted in ascending order, and then we want to somehow combine them to generate one linked list, and we return that one over there. If list is empty, we'll just return that. If maybe the node exactly is empty, like the node itself is none, we can also return that here. Okay, so how might we go about doing this? And we've done a question similar to this, right? We've done the question, merge 2 sorted linked lists, or merge 2 like sorted lists. In this case, basically, what we did is like all of this. And in this question is basically like a more generic version of this question here. Here it's k, here it's 2. So how might we go about doing this? Well, you might think of like an obvious approach, right? Let's say we had our list was maybe like list 1. So these L1, L2, etc. These are like linked lists in themselves. So one thing we might be able to do is maybe we can merge L1 and L2, and then maybe we can merge this thing with the result of L3. Then maybe we can merge this thing with the result of L4. So it would require us calling our method here, merge 2 lists, again and again. And overall, if you think about it, we're calling it n squared time. So it's a solution, but it's not the best one. It's like your worst case solution that you can do. What's another thing you can do? Well, another thing is maybe you can go through all of the linked lists, and you can go through all of the nodes and you throw them in a priority queue, a heap, and then you slowly pop out. And when you pop out from the priority queue, obviously you will pop out the minimum element, and so you can construct your list that way. So that's also an algorithm that you could use. But really, when I see this question, merge k sorted linked list, I'm actually reminded of another famous algorithm, which is called merge sort. And in merge sort, hopefully you've heard of it, but if not, let me go through the idea of merge sort here. In merge sort, essentially what you have is you have an array. In this case, or in most cases, your array is just single elements. So in our case, actually, our array is individual linked lists. So L1, L2, L3, L4, L5. These are actual linked lists, but in the regular case, it's just regular numbers. But we'll use the same algorithm here. Let's just see how it works. What we do is with the array, we'll split it in 2 halves. First half will go to the left-hand side, and this is actually a recursive call. And then the left-hand side or the right-hand side will go to another recursive call. So these two are both recursive calls. Then again, we'll go ahead and split it. We'll split this into 2. And then again, we will split it. Split this into 2. Now notice at this level that I'm on, these two cannot be split any further, right? Because they're just one element. So what do? We go ahead and we merge these together. We go ahead and we combine them. So we can combine them into 50 and 70. We essentially sort them together. Same thing here. The 30 and 10, we cannot do anything with these anymore. So we go ahead and we merge them. So you can see the merge sort. What we do is we try to, first of all, we divide. It's called we divide. We divide to the minimum case, which is single element, and then we conquer, which means we go ahead and we merge these elements, and then now we merge this again. And so we do the same thing over here, and then eventually we'll arrive at a list here, and then in the end, we'll merge this entire list together. So this is how it works. This is kind of like a tree diagram of how it works. And our case here will be exactly the same. So basically, you can think of this as our L1, our L2, our L3, our L4, our L5, etc. Something like this, right? And this is basically a linked list array. So all of these individual things are linked lists. And basically, we will divide this. So now here we might have something like L1, L2, L3, or maybe we'll just have L1, L2, and maybe here we have L3, L4, and then L5, and then we keep going. And now at this specific location, we just have L1. At this specific location, we just have L2. Now what do? Well, notice here that this is 70 on its own, right? It's not like 70 surrounded by a list here. So because our problem is a little bit different, but it's going to follow the same algorithm, if we arrive at a case where the length of the list is just 1, then we will just go ahead and we will return this item inside. Well, so what will this return? This will return just L1 in itself. Similarly, this will return just L2 in itself. And then what can we do? Then we'll go ahead and we'll merge L1 and L2. So this answer here will be L1 and then L2, whatever the proper merge arrangement of that is. And so we'll continue to do this. throughout our entire thing. And then in the very end, we're using the same algorithm. We will find a way in which we can merge L1, L2, L3, L4, and L5 together. And this one will be actually just based off of one node. So it'll be like flat like this. It won't be in an array. So let's see how we can maybe do that in our approach here. What can we do? So first of all, if list does not exist, then we can just return none, right? I will not return a node like this because it can be optional. So I would just return none here. Otherwise, let's go ahead and do our algorithm. And merge sort, it's a pretty famous algorithm, but if not, I'll walk through it to see like how it actually works. So the first thing you do in merge sort is you have our helper function. This is a recursive function. This recursive function is basically our divide function. It will keep dividing the list. So we'll pass in list here, and we have list. Okay, so let's actually handle the case. Let's not do the base case right now, but let's do the recursive cases first. So let's do the cases where we divide this array into left and the right. Well, first thing we need to do is we need to calculate the midpoint, right? So the midpoint is equal to the length of the list divided by 2. The left-hand side is we will recurse on list, but it will be from 0 to mid. The right-hand side will recurse on list from mid plus 1, or actually just mid and then onwards, because just the way Python works, this is mid plus 1. So this will be basically all of the items. So if our linked list was something like, let's say, L1, L2, L3, L4, L5, something like this, then left here would be the list L1 and L2, and then this would be the list L3, L4, L5. And notice that these are individual nodes here. These are individual actual linked lists. Okay, so now before we finish off our recursive call, now let's go ahead and do our base cases. So what do we have in our base cases? Well, we have that if the length of the list is just 1 here, then we just return the value inside. We just return the L1. We can check if length of list is equal to 1, then we just return list at 0. We just return the element inside. Now, what if the length of the list is empty, right? For example, what if like we have something like, what if we just have like L1 and maybe we have something like L1 and L2, or not L1 and L2. Maybe we have like a strange case, L1, L2, L3, but eventually, basically, the list here is empty. Like the mid is in such a place such that the left-hand side is empty. What can we do in that case? Well, if the left-hand side is empty, if not list, or we can do if length of list is equal to 0, or we can just do if not list, that's also. If not list, then what can we do? Well, then we would just return an empty list as stated over here. So this is this case over here. I'll actually put this above here. Okay, so we're almost done. Now, what about, what happens now? Well, after we're done with recursive calls, we're at this spot here. We have our L1, we have our L2. These are individual nodes. These are not arrays. These are individual nodes. So we can go ahead and we can merge those two linked lists. And we'll do that just by copying our algorithm that we have here. Go ahead and copy this. And I will paste it here. And then I will just go ahead and return this. So return self.merge two lists. My list 1 will be my left list. My list 2 will be my right list. Let me see if I missed anything. I don't think I have. So let me go ahead and run the sample test cases. And we can see we pass. Let me go ahead and submit. And we also pass. So this is actually a way in which you can do this. We basically understood the merge sort algorithm and transformed our result to be part of that merge sort. And actually this, whenever you want to like merge k things or you want to do k things, divide and conquer is a really useful strategy that you can use. Maybe even here in related topics. Yeah, so divide and conquer. So it is one of the approaches that you can use. And probably in the interview, the one you want to go for, the priority queue is like, it's not an easy thing to think about, but this is probably the most natural one you can think. Okay, now we have to fix two things. First of all, notice here that we are splitting the list, or we're splitting the list into 0 to mid minus 1 and then mid onwards, but we keep splitting the list. We actually don't need to split the list. We can actually just keep track of the pointers of the list, right? We can keep track of where we are in the list through pointers. So what I mean is, let's say we have like L1, L2, L3, L4, L5. Initially, maybe we can have a pointer like L is over here, R is over here, which means we're considering the entire list. Then maybe we find our midpoint, and then we go from L, and then mid is over here, and then we go from mid to R. So at this point, we would just consider this array. At this point, we would just consider this array. So let's see how we can do that. So I will pass an L and then R here. And what would they be initially? Well, they would be 0, and then length of the list minus 1. It will be the left-hand side and the right-hand side. Now, instead of if not list, what do we have to check? Well, we basically have to check if like the left and right cross, right? They should never cross, but if they do, that means it's empty case. So we can actually just do if left is greater than right. So maybe if we have like left over here and like right over here, if we have a case like that, then we know that we have an empty list. So we can just return an empty list. How do we check if length of list is 1? Well, we know the length of list is 1 if left is equal to right. If left is equal to right, then they're both pointing at just one index. In this case, we can just check if left equals right. Then I won't return list at 0. I'll return list at L or R. It doesn't matter. Okay? So we have that done. Now here, mid, when we're calculating mid, initially, we want to calculate it based off the entire list, right? But actually, we notice that we have left and right to tell us the boundaries of the list. So what we can do is we can do L plus R divided by 2. And now we can just change these two. These two we can remove. And now on the left-hand side, what do I want to do? Well, I want to go from L to mid. On the right-hand side, I want to go from mid plus 1 to R. So what's going to happen is mid will be maybe somewhere here. On my recursive call, I want to basically move L from, or I basically want to consider the list which comprises of these two, and then I want to consider the list that comprises of this. So that's why we move our pointers around. So when we do this recursive call here, basically our L will be here, our R will be here. For the right hand recursive call, the L will be here and the right will remain where it is. That's basically this function. So now let's go ahead and test it to see that we got the solution correctly. And we did. Let's go ahead and submit it. And it also works. So perfect. So I actually have a video on the merge to list. So please go ahead and check that out in order to understand how we merge it. But now let's just go ahead and talk about the time and space complexity. So for merge sort, if I go back here, for merge sort, the time is usually just n log n. Where does this come from? So first of all, there are n elements inside of this list here, right? And we want to split them into 2. So that's where the log n comes from. And then overall, we are going to be merging them together, right? We're going to be merging n elements together. So that's why we have an n over here. So it's n log n. Now, in our case, it's a little bit different because we have k linked lists. So first of all, it's going to be log k because we are splitting k linked lists downwards, right? And now, when we're actually merging 2 linked lists together, we don't know the amount of nodes inside of the linked list, right? So one thing for sure is we are merging k linked lists together. So we will have k here, but we don't know like the actual number of nodes inside. It's not like here, it's not like in flat list where we have access to the total amount of nodes. We don't know that. So maybe we can just call that n. Maybe we can just say n is like the number of nodes in the linked list altogether. So then basically what we have is we have nk log k. So that will be the complexity in terms of time. In terms of space, it would just be log k because we're not storing anything. We're just recursing downwards and we're doing that in terms of log k. That would be the space and time complexity. Okay,